Good morning, everyone. I'd like to start by thanking the organizers and having me here, giving the opportunity to talk here. So today, the work I will be talking about mostly is the main theme of research we are doing in our group. And we have some results so far, but there's a lot more to do, and I hope that we would get help from the audience and you'll get excited and join working in this area. So before I start, I should make sure what I mean by collections. So we are talking about image and shape collection, shape as in 3D shapes. And by collections, it means somehow they are grouped based on keywords. So you can have a keyword, like in this case, guns. You can have chairs. You can have desks. You can have other things. So there's a loose sort of grouping that's available. So that's what we start with. And during the talk, please stop me and ask questions if it's not clear, because majority of the talk I'm presenting the first time, so we have to see how it goes. Okay? So I'll start by introducing my group at UCL. So these are my PhD students and postdocs, and I'm mainly going to talk about the works done by these three people for this one. So the problem I'm going to focus on is the following. Suppose you're given an image, like a single image, and we want to understand what's going on in the room. And by this understanding, we'll start with the very obvious questions, which is very heavily studied in vision, which is labeling the objects, right? But then we want to, because we are in graphics, and we want to also have generative models, we would like to place objects there. So in this case, we would like to retrieve a sofa and place it. And by these things, the problems we have to solve is we have to find what is the object to place and how to place it and where to place it. But in graphics, there's a lot more things happening. So if you go back, you would, let's see, how do I? So you see a lot of interactions going on at these levels, which are due to illumination. There's illumination coming from outside, from here, and there's a lot of material and texture that's going on, which makes the inference problem harder and also generative problem harder. So it's easy to come up with some scenes, but it will not look realistic unless we model all these effects. And the majority of this talk is how do you look at the problem as a whole, and what advantage does it bring in if you start considering the problems in a coupled way. Okay? So this is, in a schematic way, what we would like to retrieve. We'd like to retrieve the layout of the room with the different objects that you see here, along with the structure of the object, that this is the same object repeated multiple times. And the reason they are different is due to illumination, due to occlusion, etc. Okay? So what are the data sources we have? Because for a single image, this is pretty hopeless. So we need to bring in some other priors. And luckily, as things have evolved very rapidly in the last 5 to 10 years, we have now collections of data. So this is data from ImageNet. Those who are aware of this or use this, you know, it's a very rich and even with lots of keywords and etc. available. There's also something which is less known to some communities. There's also 3D model repositories that are available. And they are growing with more and more acquisition devices coming up. And the goal is to transfer information across them. So here's a schematic overview of the talk, as it will go. At the center is 3D geometry, objects that we see. And there are certain priors that I will assume for this talk. I will just briefly show a couple of these instances, but I will not talk how we generate these priors. And then the first part of the talk will be interaction between images and 3D models. And we'll see what that means. The second part, which will be a bit brief, will be talking about how illumination and appearance interacts with the 3D objects. And the third part, which is, I think, quite different from stuff we have seen so far, will bring in dynamics of objects, and we'll see how physics interacts with 3D objects. Okay? So as some background, I will start with priors coming from shapes. Now, this is a two-slide summary of work we have done over 4 to 5 years with our group and various of our collaborators. So I will briefly show what results we have there. So this is a typical thing you will have, that we have a collection of 3D objects, only 3D so far, and what we can create are these abstractions. As you see on the left, as you are moving this abstraction, which you can think of a low-dimensional embedding, what you see are being retrieved are objects from the ShapeNet. Now, what you see here is retrieval. But what we actually have underneath is a generative model, so you can create new instances by interpolating across these shapes. And you can see that this is, if I go back and play it again, you can see that the meshing and other things can be quite different. We can't handle point cloud, but we don't need point-to-point correspondence, which is one of the advantages of this method. So essentially, we map these deformations or these variations as a smooth curves or surface in some abstracted manifold, which constitutes our shape prior. Now, this gives us a way to lift 3D images, to images through 3D as in depth prior. For a single image, you can get a depth prior of this by fusing this information. So as I say, this is the background we will assume. We will assume access to this shape manifold, which in very simple terms is if you have a few parameters, which is a low-dimensional embedding, this will generate a valid model according to the shape collection you have. Okay? So this is something we'll need. OK, so let's get back to the problem. And this gets interesting. So we are looking at a single image for now. And let's understand why this is difficult, or if this is difficult at all. So you see 6 patches here, and we want to see if they're similar or not. So if you look at the RGB level, they're of course not similar, but we would like a grouping like this, or like this, or like this. Now, this is an extremely unrealistic task for you at this moment, but if you look back the source of the data, you see the type of variations we want to capture. So on the same floor material, due to illumination, there's a lot of variation. Due to texture, there's a lot of variation for the same sofa. Or here, on the ceiling of this room, there's different variations. And we want to capture them. And the idea is to look at shape and the images at the same time. So this is the first part of the puzzle we're looking at. Okay. So this is work we did last year, and I will talk a bit more about this method. And I will stop at the parts where it's interesting technically, and also make sure that the bigger picture is clear how we achieve this problem. So what's the premise here? We have a shape collection, an image collection. And if you look at image collections, for those who are online now, you can go to Bing or your favorite search engine and search for text. So in this case, you're searching for aeroplanes. And the type of results we will get, the top few are always pretty good. They're always very well curated. So that's pretty good. But the type of things we cannot do, we cannot change the views. So I cannot ask for a query that give me this aeroplane rotated by 30 degrees. This is the type of query we would like to support, and we can support by what we do. Okay. Now, for the second part, if we now go to the shape collection, the story is not so great. If you look at here, and these are planes, of course, these are planes. There is also like 2D planes as having two triangles constituting a quad. That's also a plane in a certain way. So we have all these ambiguities, and you'll see only very few of these items are green as being valid. So to summarize, the situation we have is for images, we have certain greens and certain crosses, because some things are good, some things are not. You can't change view and geometry. For 3D, it's complementary. So the obvious thing we would like to do is transfer information across. Okay? And the challenge is we want to do it in an unsupervised fashion, which makes things difficult. The level of supervision is coming from the keyword. But after that, it has to be unsupervised. Now, in the general domain of image search and shape search, and there's many experts in this audience, there's decades of work on how to attack various parts of this problem. What is novel in this work is establishing these explicit links across the collections. So what are the key ideas? There are 4 main steps, and some are more like steps, and some are more like insights. The first one, which is quite standard by now, is we want to use the image information to sort out the 3D models. Then we would like to do the co-alignment of these 3D objects. By co-alignment, you mean if you are given, say, thousands of models of 3D models of planes, they are not mutually co-aligned. That means one might face this way, one might face this way, etc. And we have to bring them to a consistent alignment. The third one is we will push the information backward. And finally, we can do some shape attributes on the images. So it will allow us to support queries like, give me the plane that's rotated by 30 degrees, but also give me the plane that's wider or fatter, etc. Okay. Now, technically, the first part for the co-alignment, it turns out that once you start looking at the problems with the structure of the problem, it amounts to an extremely simple reshuffling algorithm, which we'll talk about. This part, I think, is most interesting technically, where we will map variations to variations of SVM planes or hyperplanes. And the third part, about the shape attributes, it will be a regression I'll talk about. Now, the reason we can do it at a very large scale is the algorithm does not try to establish any point-to-point correspondence. So this is extremely key. And this is the reason of success for this method. We don't do any background subtraction, and the links are very loose links. There's no point-to-point link. It's image to model or model to image links. OK, so let's start with a quick preview of the system. So what you see at the beginning is the images are used to filter the 3D models. Green is shown just for visualization, so you get the model sorted. And once you have that, you can go and co-align the model. So now you see all the aeroplanes are pointing in the same direction, and the right side's in 3D, so you can rotate them and do other things. And now you can push information from the right to left. So you use the right information to align the images, but now they're aligned by pose. So the chairs are sorted by etc. And then later we'll see you can also do variations by shape. So you can sort now the chairs by their relative heights, or relative width. It's quite coarse, but much beyond what you can do otherwise. By the way, all this code is online, so you can download and try. I will not suggest to you that you try now, because it's quite heavy to download the data. OK, let's look at the method. So the first part is by now quite standard in computer vision community. With the recent success of various learning approaches, what you do is you have access to 3D models. So you use the 3D models to render candidates from different views. So if you see in the next slide, you take this model along with the texture available and render it from different views. So you have the same object observed from different view, and then you also have out-of-class models, and you use it to train a classifier. In this case, we used a Hawk feature, but now you would use CNN, because this was a couple of years back. And then you use it for coding it, and then you have this positive and negative examples. By that, I mean you have many instances of chairs, but you have also instances which are not chairs. So these are the plus and minus examples. You use them to train a classifier, and that's enough to sort the results. So there's nothing deep going on here. So here's a typical example. These are the original 3D models, only part of them, and this is the sorted one. Okay. And of course, it's better than doing it directly based on shape signatures, for reasons detailed in the paper. There's more plots. Generally, top and this corner is higher, and the dotted lines are pointing in the right direction. So that's good. Now, the second part, it gets interesting already, technically. So the problem we are now trying to solve is we have these good models of this class, in this case, cars, and we would like to get them consistently aligned. Now, for about 3 or 4 years, we have studied this problem, looking at 3D models. And there are many algorithms on co-alignment and spectral analysis, which works nicely, but it's complex to do it in a very large scale. The realization we had is once we have images, this can be a very, very simple, almost embarrassingly simple problem. So what's the main idea? Because they are all 3D models, we can render them in different views. Okay? We can render them for all the objects. Now, when I talk about the view classifier, I have to be careful to avoid any misconception here. We're looking for a 1-degree variation. We assume that the up vector is fixed, so we are trying to say from which angle I have seen it. Okay? Now, then what interesting thing which happens is it's almost like solving what you call one of these number puzzles, that you have these rings that you are rotating, and as soon as the one alignment is done, all the subsequent ones are done modulo 360, whichever degree you have. So essentially, we are trying to solve this type of link, so which means this V2 corresponds to here, which would indicate this corresponds to here, etc., and then you mod up. And this is what we are solving for. So for each case, this is we are solving for an offset, these green offsets. And this you can write down at a very simple optimization modulo this 36, because we sampled by 10 degrees, so 360, and then you can solve this, and this works beautifully directly at the rendered image levels. Okay? So we have them consistently aligned, and now we go for the view classification. What does that mean? Now we can push back the information. So what we have is all the 3D models are consistently aligned, but now I can push it back to the images to give view estimates to the individual images. And that's what we're going to do. Okay? Now, there's something subtle that will go on here, so I will try to go slowly over this. So what we have are views of these models. So I don't have one car. I have thousands of cars, but I know 0 degree for all of them, 10 degree for all of them, etc. Okay? Now, for each image, you can get your feature vector. We use these Hawk features, but now you maybe use your favorite CNN features. And then what we are interested is tracking the variation across view, because they're ordered. So these feature vectors can now be tracked across views. So it's not a single feature point, it's a track of a feature points, where each point has a theta associated with it, or a degree associated with it. You can think of this as a regression problem. Now, the final step, which is a key one, is we map this to how the SVM separator plane will be moving across the view. Okay, so let me explain that one more time. So if you are for a fixed view, you can train a SVM classifier using your positive and negative examples. And for those who are familiar with SVM, this amounts to detecting the parameters for the hyperplane. Now, we don't have a single point, but the points are moving across view. And we want to see how this SVM classifier plane is changing subject to this view change. So as a result, we have a direct way from getting a feature vector to an estimate of the view. This is, I think, technically quite interesting. So here's the results. So this is a 3D model. These are the top image candidate estimated for that view. And you can go on and do the same for different views. Okay? So here's a very interesting insight already you get about the data set. So you ran it for our data sets, and we get these type of plots. So I have to explain this a bit. Higher the height means there are more images for these views, which starts to make sense. For bicycles, this is the common view. For cars, you have the 2 common views, and this turns out to be the standard views you have in car shows, this -40 and +40 degree, same for chairs, etc. And you can do further analysis on that. And finally, we push this information back to the 3D attributes, because now we have view aligned, both in 2D and 3D. In 3D, we can measure shape attributes, so we do something similar to push it to images. Okay. So here I will show the system again. I will explain what's going on. On top is a 3D icon. There's no model in this case. So this links all the 3D information, 3D models here. Sorry, these are the images. This is the icon of 3D. So as you move the icon, you can say, OK, give me the view for here, and it will give you the images. And then we can also do this based on attributes. So the first part is quite simple. You rotate the view, and you get images for that angle. updated. So now you were transferring information from images to 3D and back to images again. This is the interesting bit. So now you have locked a view, and then here it might be hard to read from the back. It asks for car which are wider and less narrower. And the way it does is, this is some attributes which is easier to make a measure on shapes, so you push it back to the images. And then you can stop, and you can again change the view, and you can keep going back and forth as you want. It's quite fun to use this. Now, there are some severe limitations which leads to follow-up work. We don't handle background clutter. So the way we assume that there's a relatively clean background, so they are just averaged out. We don't do anything specific for that. We have limited shape attribute support, as you said, because we have a severe projection going on, so we can't do beyond this ratio of height and width, for example. Not fine scale details that we would like to have. No explicit links. So this is an advantage, but this is also a disadvantage. If you want to do some part level edit, you can't do it with this level of abstraction. And in this work, we only did 1D view. You can extend it to 2D view now that we have more rendering power. Okay. So with that, I move to the next part of the talk, which is doing illumination and appearance. And this is a very interesting insight that we came up with that I think solves a very important problems in graphics. For those who are interested in graphics, this is a very important problem to solve. But the method is extremely simple, as you will see. And here is something, this is my very personal thought, that sometimes very complex problems can be made very simple if you break the right assumptions, or if you realize what is the limiting assumption and you try to break it. And maybe it's easy because this is often a first take at the problem, and that's what it's easy. But you have to, it takes certain observation to get to the right insight, I think. So to me, if the method is very simple to use, it has the advantage that it can be scaled very drastically, as you will see. So what's the problem? And for those who work with 3D models, you might be aware of this problem. So we have lots of 3D models available, but they're not always textured. So if you search on TurboSquid, you would notice that if this model is not textured, it might be free or maybe $1 or $5. But if it's properly textured, it might be $100 or $500. Because it's expensive, it takes art to do it, and they're not so simple. What we observe is there are lots of images available of models, and can we not transfer the information from here to here at a very large scale? So here are the images of chairs that are available. I really like chairs, and there's, you can see this. I found out that I'm not the only one who likes chairs. There's a faculty at Berkeley, I think in the 1960s and 70s. He wrote a book on chairs, and it's something interesting to read. Okay, so how can we do the transfer? Because this seems quite hard, right? We have to do something right to get it. So what's the problem? We have images, we have shapes. Note, I say we have similar shapes. It's not the exact shape, because I know when I do the retrieval, I will never get to the same shape, something similar. Okay? And then the output will be this textured model. Now, it really depends on on what you want to use it for. Like if you were talking to Pierre for texturing or for parameterization, this will be not acceptable quality because this is very low quality. But if you're talking to someone in computer vision who wants to use for training, this is much better than this one because it has something more realistic. And we'll talk more about this later. Of course, we don't want to do it for single objects. We want it for the whole collections to be textured in the same way. Okay? So what are the challenges? The challenges, we are all aware of the challenges. The challenges is the geometry varies. The shapes are not exact. There's illumination variation, right? And these are the things that makes it difficult. And again, in the whole domain of texturing, shape from shading, etc., there's a couple of decades or maybe 3 decades of work on that. What makes it different is since we work with textures, we really have to model the illumination and the texture at the same time. And this is what was somehow missing in the previous work. In the paper, we have probably huge amount of comparison for the different methods. If you're interested, you're welcome to look at that. But I will focus on the main idea here. So the main idea is we're not going to handle all chairs, right? We're going to handle chairs where there is some repeated texturing. And this is what we are going to explore. Because then what we are trying to solve is what is the texture patch, what is the fabric that was used, and how it was oriented on the surface. That's all we need to know. So we need something very simple to extract from that, which means we can deal with a large amount of noise. Because if we can extract out from which part to copy. So for example, if you look at this table, this is a good part to copy. Maybe this part is not because it's getting a lot of highlight, or this part is not because it's getting a lot of shadow. And we can do that because we have a very crude 3D approximation available to do some of these reasoning. That's at a very high level, that's the main idea. These are things we will not be able to handle because here the repetition is at a scale which is beyond what we can handle. Okay, so let's move on. So this is what I have explained. And the main thing we wanted to have is this should be fully automatic. This was a driving force throughout. So what we do is, we have seen this already before, we extract a shape that is similar and very similar to the crosslink that I presented just before. And then, given the shapes, we can retrieve 3D models along with the pose. Again, as I said from the last work, this you can consider to be fairly standard by now, and you can get reasonable output as long as you are not very picky. By that, I will assume that the results are close but not perfect when I go to the next stage. This is important today. The main thing comes as illumination correction. Let me explain what that means. And here, the approximate geometry is going to help. The approximate geometry gives me depth maps and normal maps, right? So this is good for rendering. And then what I'm going to do first is I will extract parts of the 3D model, since I have depth information, that have less distortion. So I would like to prefer flat regions versus somewhere where it's very extremely curved, because then I have to rectify it. Now, it might seem that if I have a curved region, since I have the curved region, why don't I rectify? It seems this should also be a very fairly easy problem. But we don't have a good geometry to start with. We know that the geometry might be different from what it actually is. So this can do more harm if we try to correct these regions. Hence, we are looking more at planar regions where these artifacts are there. So here a different, I should go back. OK. Maybe it's set to auto. OK, so as you see here, we extracted these. These are rectified, but then you can see that they are not of the same illumination. So we have to correct for the illumination. And again, this we can do in a very nice way. We can set up some sort of a basis. It's not in the right sense of the word basis, where you rendered the view or the object under fixed illumination from different ones. So effectively, what we are modeling is we are modeling this room as a superposition of individual light positions. That's what we're doing. So what it does nicely it gets the different shadow effects, which is quite nice. And then you can set up a simple optimization in terms of the basis. And what it shows here, we have a L1 regularizer here that eventually it will select these modes. And each mode corresponds to one of these things. And by this, I know where the light is, because I have rendered the scene. So it explains this image as a combination of these 4 spotlights, if you will. That's great. It doesn't look great when you see here, but it doesn't have to be, because all I'm doing here is an illumination correction, which I'm going to use for extracting out the patches. This is a step which is a bit more involved, and I would just explain the high-level idea. What we do is, once we have the patch, we find out by these green and red arrows how they are locally aligned. Right? So this is a very classic parameterization problem. Again, you can see, obviously, we are making use of the geometric prior to derive this rectification. That's great. And then we are pretty much done, because then we can transfer we have extracted the patch, corrected for illumination, and we have extracted also how they are laid out. So synthetically, I can go ahead and generate these renderings. Okay? Now, the beauty of the method is you can do it at very large scale. So I can't fit in here, but I will explain what it is. On the top is almost like thousands of chairs, but without texture. This is already from the result slide, so they are already textured. And then on the left are these thousands of images that you have pulled off chairs. And then I would like to populate this product space. So for each model, I would like to texture with all the variations. So what does it mean? This is what I would like to have. A bit more than that. Now, remember that in each case, we are not only getting the textured model, we are also getting a set of good illumination setting that's recovered. So for generating training data, this is extremely exciting. Okay. So it's really big, this data set. So you can go in here. You can do it for other data sets, and there's lots of comparison in the paper. I will leave it out. One thing I want to show is this illumination correction is extremely important. And this is the insight that took us a while to figure out. If you don't do illumination correction, the texture patch will be messed up, because, of course, correspondence will fail. Right? But when you do the rectification and the illumination correction, you get a much more consistent one. If you look closely, you would notice that this is not exactly the fabric you expect. But for the results we would want, this is good enough for us for now. Now, I do a lot of research looking around, so which means if you look around and see, is this a scene I can parse visually? That means there is some hope for us to do it if we capture the right models. There is a dependence on paths, and by path I mean along which shape you propagate the shape, the texture, and these are just some examples of that. And you can see that at the first glance you don't see the differences, but then when you look at the seams, it's an easy way to see that there are some subtle differences. I'll leave out the comparison for the paper. This is here. The main message I want to convey, there are maybe 3 things that are very important. Correct for illumination. Don't try to do point-to-point correspondence, because that is extremely hard. If you can do it, that is the right thing to do, but we would not like to do it. And account for in the model that you only have a rough geometry and pose estimate, because we have made immense progress in pose estimation and model estimation, but it is not perfect, right? So even though the results look very perfect on paper, you would never get the spot-on result. So if you make sure you handle this ambiguity in the data or in the algorithm itself. Leave out the comparison. I work a lot on editing images. I really like playing with Photoshop, and I can see this being something that totally ends up that you have an image, not a 3D model, and a shape, which is 3D model, and I can see a rendering workflow that combines them to create such image effects. Right? And this is how you can do it. It's detailed in the paper, but you can see you can capture subtle effects of how these illuminations are. And this is with a very simple rendering model. For someone in the rendering society, this is a rendering equation in 70s, as basic as it gets. Okay? For those in vision, this is something I hope will excite you, which is this is training with no texture, training with our texture, right? And you can see the performance boost we get. This is for depth estimation if you have this textured model, which is extremely believable. This is how we started with. I think this was as a background. This is how we started. We needed to train certain networks, and we found that the real images and the models we have are far from being same. And this is, if you want to use these models, you don't have to implement the algorithm. Also, although the code is available, but all the textured models, the ones I showed, along with the Blender setups for the illumination, are available. So you're welcome to download and try them for you. Now, the last part of the talk is going to talk about dynamics. Okay? Let's start with a very mini quiz. Right? These are 2 patches, and these are 2 patches we have seen here on the first day when Pierre was giving the talk. And if you look at the level of the image patches, they look exactly the same, right? But if you look at here, go back and forth, you see this is from the board here, and this is where he blended in with the background, etc. This is very difficult to capture. So the next agenda I have, and this I'm quite excited about, is what can you learn by seeing the scene over time, right? And this is not just video processing. So let me show an example. So here is in our lab, we have a red curtain, and we throw an objects at each other. So let me do it again. So this is a rugby ball hitting our favorite rubber duck, right? Why do we want to do this? It's a lot of fun. So we spend hours capturing this because if you try to throw this, it will just go through. Two motions, it would not hit. But why is this exciting? Because I think what we can do is, the goal is, what can we learn about the objects by looking at them? And by learn as not doing reconstruction, but learn about physical properties of the objects. So for example, when I hit the table, based on our experience, I can tell when, we can hear also, but I can tell by my interaction that how is this material. I can tell about the stiffness of the material, etc. And that's what we are trying to do. We want to learn or infer parameters of collisions. So these are what we are interested in by observing video sequences, single video sequence. This sounds quite like an academic exercise for now, because this sounds great, but why would you do it? I think the plan is to push it further and further along. How much can you get by observing sequences? Which is quite interesting, because these are typically measured other ways. So coefficient of restitutions are measured other ways. As a very, very simple premiere to collision detection, what we have is the tracks of the object over time. These are not point masses, so if I throw this, this would actually spin. So it has angular momentum with it. It should be fairly clear, we cannot recover absolute mass, but we can recover mass ratio. That's what you're looking at. And we're going to recover what is called coefficient of restitution, and I want to emphasize that a little bit more. And again, like in the previous part of the talk, we saw that we don't try to establish point-to-point correspondence. In this part, we don't try to do the complex thing of resolving collision at time of collision. As you saw from the curtain example, the collision time was completely masked out. So we have information before and after collision. OK, let's move ahead. So coefficient of restitution is quite simple, which means like if you drop an object, how much it bounces back. And this relates to how much energy is lost in sound and heat and other things. There's a specific definition for that. So you imagine there are two objects colliding, the green and the blue ball, and it collides. Okay? And then it goes away with a certain velocity. These are indicated. And it can be derived based on the energy, or it can be derived at the relative velocity before and after collision. Okay? There is a slight complication to that. You have to take this along the normal direction of the collision, which is here. Note that this is the normal at the point of collision, right? So this is something which is hard to do if you do a forward simulation, because you can easily go off. And I talked with a few of you in the last days about this. So we leave it as an unknown and infer it from that. OK, let's go to the physics of it. And I'll try to keep it simple and try to get the main ideas across. There's two things you have to worry about: before, after collision, and during collision. Okay? Now, before and after, so if you leave out this part, it's going to be projectile motion. This physics is quite simple. You have tracks. This is very simple parabolic equations for this. But the priors are, these are parabolas. And I know that the gravity vector, so I know G, so that's known. So this helps a lot in the fitting problem. And then at collision time, then the blue and the red curves, so approach and going back, they have to agree on one point, of course, because you hit and come back. But for two objects, they would not agree, because they have physical objects. There will be a difference. But of course, you can, again, find a geometric argument that this object plus this object should be equal to this size. Right? So these are constraints that will be very useful. Okay. And you can write out the necessary angular momentum. So this is moment of inertia transferred to the frame of the unknown rotation, et cetera. And this is the angular velocity. So these are things that work out. So these are quite messy. It took us quite some time to get it right. But you have to believe me that this is not the hard part. you can write it parameterized in terms of the rotations, which are the unknowns, the omegas, which are unknown. So these are the things you can set up. Interesting thing is moment of at point of collision. So this is where the collision happens. And this at point of collision, what we do is we neglect gravity, because at that instance, there's no external torque in the system, so linear momentum is conserved. So this is the linear momentum before and after. And the more interesting thing happens with the angular momentum, because this has a moment of inertia with the angular velocity, plus you have to also account for the torque coming from this displacement. So in this, if you were setting this up, hopefully you don't have to set up, you can just use our code. But if you have to set it up, you have to be very careful with your choice of system. Because here, this distance starts to matter, and if you do a wrong choice or inconsistent choice, this constraint will not be satisfied. And some technical details, you can transfer the moment of inertia with respect to the rotation from time zero. Okay, there is one final thing, which is energy is not created. That with energy before and after will be good. So the after energy will be less. Okay. So this you can write in a classical way in terms of impulse, which is this Jn, and that's the main thing you need to know. And then we can immediately move to some results of how these constraints help to solve it. I think I'll skip this part, and I will show you the more complex results. So here's the first validation, which is we are just going to drop balls. Right? So here you drop it. And the reason we want to drop these balls is if there is no spin on the object, then the coefficient has a very simple formula to account for. Sorry, it went a bit here. So based on the drop height, you can estimate this. And we did this verification, and you can see that the coefficient of restitution we observed is quite consistent, even if when the object is spinning, where the formula fades. Okay. So let's see this video here. So these are the reconstructed results, right? And here are the mass estimates from this. And this is all the input that we had. This gets to more interesting one. This is my bike helmet with again, the rubber duck. No, this is the first elephant and the rubber duck. So we have lots of these toys in our office now. And you have to compare them visually how it is. And it's not that, remember, it's not recovering the collision sequence, it's also recovering the numbers, which are quite important for doing actual simulations with this. So this is the input here, and this is the recovered one, right? So it's not only recovering the reconstruction of that, it's physically correct because it follows all the equations that we wanted to do. And now let's move to the final one, where we go back to this curtain scene, because this tells us, technically this is quite hard, because you don't have the corrections around that, and you can see that the rugby ball spins quite a bit. That means you have to account for this. Right? It even spins, I think, once or twice behind the curtain, and you have to get it right. Okay, so that's the picture I showed. As future work, I think there is tremendous potential of bringing in the human actor, because as I walk around, if I do scene, I give you a lot of priors about the scene. And also there's a lot coming up in terms of sensors, because now we are moving from the single camera to two camera, and I think this gives us a lot of additional cues that can be used, even though this is narrow baseline, but I think still it would give us a lot of depth information that can be quite useful. And I'm happy to talk a lot more about this as you move on. A thing which I haven't heard a lot in this conference so far is about deep learning, because we are getting a lot of that. And I think that will also come into the picture a lot by providing priors in terms of, even if it's just a unary term. Okay. So I will briefly talk about the references. So the first one, and I highlight the people outside our group who are our great collaborators on this. So the first one was this crosslink. The second one we are presenting next month on these transfer of texture from images to 3D models. And the third one is also we are presenting at the same venue next month. And all the code and data is available on our website. So please go there and download and use it. If you have questions, please write to me or any of the students. We'll be more than happy to help you. And we try to respond pretty quickly. I'll take this opportunity very quickly to advertise that the next year SGP is in London. It is now officially approved by Eurographics. So I hope to see many of you at this venue. And with that, I'll be happy to take questions. Thank you.
So we have time maybe for a quick question.
So I would have a question on deep learning. You mentioned this at the end, because I noticed deep learning is progressively, for instance, for texture synthesis, is giving at least as good result as traditional method. And do you think it will be also impacting shape analysis, shape modification?
I think if it gets to that, so this is a question I think a lot these days. For some of the tasks, I don't think this is going to be so easy because of lack of training data. Right? The second part of the talk is almost like creating training data for deep network. Right? But in the long term, it's not about whether we have traditional methods or deep learning. Right? I think it's how do you combine them in a smart way, because I think, as you know, that we don't quite understand even the CNN framework, how it works and how it optimizes with so many variables. And if the more we understand, I think we can speed up the time, the training time, and also the memory requirements, because these are quite insane right now, and it's not easy to imagine that we can do it at university settings at very large scale. So I think it's going to be quite exciting to see how we can cleverly combine the two. Right. And not as output-input combination, but really at the method level.
Okay, no more questions? So let's thanks again, Niloy.
Yeah.